Well, hello again, 3C, and welcome to another exponential decay lesson. Today we are going to create equations for exponential growth or decay situations, and I know the difference between them. So, can you pick out a growth situation as opposed to a decay situation? So, growth or decay? Decay or growth? That is the question we are dealing with. All growth and decay questions follow this basic formula, where the current value is y, or some other more appropriate variable that we stick in there. The a is our starting value, b is what we're going to multiply by every time. If it's growing or decaying, we have to decide how we're going to tell the difference, and x is the number of time periods for those decay and growth sections, so the number of decay or growth periods. For a situation to show growth, the number we multiply by every time, the b value, this one here, has to be, well, it has to be bigger than 1. Bigger than 1. For this situation to show decay, means it's going to get smaller and smaller, it has to be less than 1. And by less than 1, we're not going to go way less than 1. It can't be 0 or in the negatives, so not negative. Even though negatives are less than 1, our b can't be negative. Okay, so example number 1. Here we're going to figure out whether these represent growth or decay situations. Or, I've also got the option here, neither. Okay, so let's have a look. Y equals 12, 3.57 to the t. This definitely looks like one of these situations where it has something equals something times b to the x. Okay, this looks like it. So is it growth or is it decay? Here's the big indicator. This number is bigger than 1, which means that it must be growth. So I'm going to put a little arrow there and say that that is greater than 1. So this is a growth situation. This one over here, same thing. This number here is bigger than 1. So this must be a growth situation. Now when we get over to here, there is no exponent. Okay, none whatsoever. This is a neither situation because there is no exponent. You can't have an exponential without an exponent. It's in the name. And lastly, this one looks exponential. We got an exponent of t here, and if we take a look at what that t is on, that, my friends, is less than 1. So this is a decay situation. So now we're going to have a look at a couple of more situations here that maybe have slightly different questions. So example number 2, a computer you bought, and we're going back to computers again because they depreciate in value quite extensively. A computer you bought for $1,840 depreciates at a rate of 3% per week. Write an equation to represent this situation if V is the current value of the computer and N is the number of weeks you have owned it. Okay, so writing an equation, well, V is the value. Initially, I paid $1,840 for it, and remember what we're looking at is y equals ab to the exponent x, where a is our initial value. B is what we multiply by every time. Well, since it's depreciating by 3% per week, that means that it keeps, what percent of it does it keep? Well, if it loses 3%, it keeps 97%. Or we can think of this as b equals 1 minus 0.03. So we do 1 minus that. Either way, it's 0.97 that we're going to multiply by every time, and n is the number of weeks you've owned the computer, so that's n. Write an equation to represent the percent, p, of the original price of the computer n weeks after it was purchased. Well, p is percent. Now this time our initial value has to be the initial percent. So initially we paid 100% of the price. So we're going to use 100 in where the A is. The B is the same thing, 0.97, and an N up there. All right, Next one, it says, how long will it be before the computer is worth only half its original value? Now I have a choice. These two equations represent the same situation. We want to know how long before it's worth half its original value. So we have a choice here. I think I want to choose this one because half the original value is 50%, and that's just a little bit easier to think of. This is going to be 50 in here if it's half the original value. So if I put 50 in there, and then that will equal 100, 0.97 to the n. Now the n is really hard to solve for. Okay, in fact, we don't solve for it in this course other than to do the dreaded trial and error. So here's what we're going to do. The first thing I'm going to do is get rid of this 100 just to make it simpler on both sides of the equation. And if I get rid of that 100 by dividing both sides by 100, it's gone on this side, and this side is 50 divided by 100, or 0.5, equals 0.97 to the n. Now what I'm going to do is I'm going to start by trial and error and figuring out what value I put on n to get to be 0.5. So I'm going to write out some of my trials over here. So let's go 0.97. I know it's not 1, because if it's 1, it's just 0.97. And it's going to have to be a little bit. So let's try 0.97 to the 10. And we want it to be 0.5. So 0.97 to the exponent 10 is 0.737. So it hasn't been going long enough to get half the original value, so it's not going to be 10. What about 20? 0.97 to the 20. Let's see what that equals. 0.97 to the exponent 20 is 0.543. 0.543. Okay, so we're getting closer. That's pretty close. What about 25? 0.97 to the 25. 0.97 to the 25. 0.4669. 0.4669. Now I've gone too far. So it's got to be somewhere between 20 and 25. 0.97. I'm going to try 23. 0.97 to the exponent 23 is 0.496. 0.496. Now you can see that that's still a little bit too much. So that was, and that was to the 23. So I'm going to try to the 22 and see what that is. So 0.97 to the 22. And that's too much. So 23 it is. We're going to say at 23 weeks. So there's the answer to our question. N is about 23 weeks. So after 23 weeks, it will only be worth half its original price. And that's about 2 years, a little less than 2 years. How much would a 10-year-old computer be worth? So we're going to go up to here. I'm going to use this one because we want value. So 1840, value equals 1840, 0.97 to the 10. Because it's 10, oh, not to the 10, because this is in weeks. So it's not to the 10. I'm going to look up here. N is number of weeks you have owned the computer. So in 10 years, how many weeks will we have owned the computer? Well, N is going to equal 52 weeks in a year times 10 years, which is 520. That's a big exponent. Let's just stroke out what I have here and put in 520. Now let's pull up that calculator and see what it's worth. So 0.97 times, or not times, to the exponent 520 times 1840. And that's 0.0002. 0.0002. That is not even a penny. Okay? That's not even a tenth of a penny. You would need 10 of these computers. Yeah, never mind. It's worthless. basically. Okay, this is so close to nothing, it might as well be nothing. So therefore, it really isn't worth anything. And there's not too many people that would buy a 10-year-old computer. Next question. The half-life of radioactive element plutonium is 25,000 years. If 16 grams of plutonium are initially present, how many grams are present after 1,250,000 years? Okay, so let's make an equation. Let's call it the amount equals the original amount, 16, times, what's our b? What are we multiplying by every time? Well, here's the word that you're looking for. Half-life. It's a half-life, which means it's a half that we put in there. And if we put an n up here, that is the number of half-lives that have passed. So what this situation says, it starts with 16 grams, and in 25,000 years, it'll be 8 grams. Okay? And then in another 25,000 years, it'll be down to 4 grams, etc., etc. So we have to figure out, what do I use for n? How many half-lives are there in this thing? Well, let's do a quick calculation over here. N is going to equal the number of years, like this, divided by the number of half-lives, or divided by the half-life. And this will give us how many half-lives we have. So 1,250,000 divided by 25,000 equals 50. So it will have cut itself in half 50 times. So 16, 0.5 to the 50, and let's punch that into our calculator. So 0.5 to the exponent 50 is really, really small. Times 16 is still really, really small. 0. How many zeros were there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros and a 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros and a 1. Now your calculator may have given it to you differently. It may have said 1.0 times 10 to the negative. We had 13 zeros and one more, so it's going to be negative 14. Because I have to move that over to here to figure out what that number is. That might be what it gave to you. In other words, there's not much left, and this is in grams. If you thought the last one, the computer value, was close to 0, this is even closer to 0. So therefore, almost no grams are left. And that is the end of this video.